My name is Mike Pilastri. I'm going to talk to you a little bit about neglected tropical diseases. These are infectious diseases that primarily affect the developing parts of the world. And the reason they're called neglected is because when you consider that drug discovery of new medicines is very, very expensive, when you think about the population that get these sorts of diseases, they're very, very poor. And there's no financial incentive to invest all that money in drug discovery. And so what we end up with are what we would call neglected people, these that suffer from these neglected diseases. This is not a minor problem. So you can see across the equator, you can see the darker colored red parts of the globe have more of these endemic tropical diseases. And you can also probably note that most of the dark red countries are some of the poorest in the world. About 1 billion people, just over 1 billion people, have one or more of these diseases. A couple billion more are at risk of these diseases. This is not a trivial healthcare problem. Yet, because of the poverty of the folks who contract these diseases, there's no desire or there's no energy behind the system to get new drugs out into the clinic. This is one of the reasons that I left industry 10 years ago. I wanted to work in a nonprofit environment, to work on diseases like this where the profit motive is not existent. So on this slide here are shown 4 of the deadliest creatures on the planet. We have the sandfly that causes Leishmaniasis. We have the mosquito, which causes malaria and dengue fever, among other diseases. We have the kissing bug that causes Chagas disease in South and Central America, and then the tsetse fly that causes human African trypanosomiasis, commonly called sleeping sickness. If you take a look at malaria, we're talking about over 200 million cases a year. Furthermore, almost 500,000 people die from malaria every year. 500,000 people, and the majority of them are children under the age of 5. If you think beyond the death that ensues from these diseases, you have to think also about the morbidity, quality of life, because when people are sick, they're not working, and this reinforces the cycle of poverty. The diseases caused by these 4 insects alone leads to 5.2 million years of quality human life lost. This is not a small problem. So what do you do in a resource-constrained area of drug discovery? Well, it was stated very clearly that the best way to discover a new drug is to start with an old one. And in fact, if we look at some of the drugs for the diseases I just highlighted, drugs like amphotericin, which is approved in the developed part of the world as an antifungal agent, is now being reused as an anti-leishmanial agent. It's a frontline drug. We look at a drug like ivermectin, which we all know if we have dogs. This is HeartGuard. It's used for deworming. This is also a very effective drug for killing the parasites that cause river blindness, which is the #1 source of blindness in the developing world. And the use of ivermectin has nearly eradicated it. Eflornithine was originally discovered as a cancer drug. It didn't work out. It's now used in the developed world as a topical agent for hair removal. But now it's used as an intravenous drug for treating sleeping sickness. So we can repurpose drugs and use them directly. So drugs that are already approved, and then use them for a different indication like parasitic diseases. However, there's a trade-off. You get a drug that works, but it has side effects, a lot of side effects, because it was originally designed to do something completely different, and so you would expect to have some side effects. So what my lab does is we go about the problem slightly differently. We start repurposing, but we use that not as the end, but we use it as a means to the end. At the risk of giving anyone flashbacks to organic chemistry, this is the molecule called lapatinib. It's on the market as Tykerb. This is a breast cancer drug. I want you to focus, for those who are fearful of chemical structures, focus on the center. What we do is we take a drug that is FDA approved, we test them against parasites, and then we re-engineer them to be more active against parasites without killing human cells. So this compound was discovered in collaboration with a team at University of Georgia to be effective at curing sleeping sickness in mice. So what we did is we started to re-engineer the structure of this compound. So the center is going to stay relatively constant. We make small structural changes to this compound. This compound is a very effective Chagas disease agent. We make more structural changes to get to this compound, which is an extremely potent anti-malarial compound, which is now being tested in animal models. This compound here, again, minor structural changes to get to this compound that is active against Leishmaniasis. And finally, this compound here, minor changes, morphing into this to get a drug that is active against sleeping sickness. And this compound is also effective in animals who are infected with sleeping sickness. The important part here is that we were able to take the compound that was actually kind of toxic to human cells and re-engineer them so they're non-toxic to human cells and very effective for these parasitic diseases. We don't do this alone. We do this in collaboration with many other labs. This is only a subset of them. We partner with drug companies, we partner with the military, we partner with other academic institutions to bring all sorts of angles that are required for effective drug discovery. And we at Northeastern are the center of this. We harness these collaborators together around medicinal chemistry to bring these projects forward. This is just one of many infectious disease programs going on here at Northeastern University. We are committed, this is a major focus of our drug discovery efforts at Northeastern, we're committed to finding the next generation of drugs for those suffering from infectious diseases, particularly the very poor. Thank you.